today's class. I will discuss about the rest of the class content regarding the Smith charts and the series stub matching in Smith charts. So series stub matching, series stub matching using Smith chart. So Smith charts. So series stub matching is basically connecting a series stub in series stub in series to the load when there's a transmission line like this. So the stub will be this component. This will be the series stub. This will be series stub, right? And this stub needs to be placed at a certain location, D1, let's say, from the load, right? So, and the length of the stub must be also defined. The length of the stub L1 we will define also using the Smith chart. Okay, so normally the width of the stub, it is like depending on like a fixed value that is given in the standards. So we can use the given standard for defining the width of the stub. So the width of the stub will be defined using the standard method, standards of the standard ways of standard width value that is used in all cases. So the width will not be a varying value based on the load. So width will be constant value for many, I mean all series stub matching. So we will be not considering the width calculation. We will be deciding D1 and L1, the distance to the stub, and the length of the stub. So these are the two parameters that will depend on the load value that we consider that is connected to the transmission line. Okay, so in this procedure we have to follow a certain number of steps, just like for the shunt stub matching. So first step is to normalize the impedance. So if we consider the impedance of the load as capital ZL and its value as 100 plus J80, then the normalized impedance value we can take by normalizing the load impedance. So if the characteristic impedance is 50 ohms, what is the normalized impedance value? How can we find it? By doing what? Yeah, so we need to divide the load impedance by the characteristic impedance. So the load impedance here is 100 plus J80. So we will divide, we will divide each of these by 50. So this impedance will be divided by 50, which will give us 2 plus J 1.6. So this is the normalized impedance value, and the Smith chart is defining the normalized impedance values. So in the Smith chart, you are only pointing out the normalized impedance values. Okay, so in the Smith chart, you need to find the location where you find this normalized impedance value, right? So if it is like 2 plus J 1.6, then that point it will be in the upper half of the Smith chart, right? So you need to find the circle which correspond to the value 2, which give us the real part of the impedance 2 plus J 1.6. 1.6 line you can find using this one of the lines in the upper half of the Smith chart, and then you will be able to find the intersecting point. So this intersecting point will be the normalized impedance of the load. So I will represent the normalized impedance using a simple ZL. And another important thing is, for series stub matching, we will be uh, considering the Smith chart as a impedance chart. So for series stub matching, we will consider the Smith chart as a impedance chart. Okay, so the reason is, why do we consider impedance chart, right? So the reason is, like, we are going to add some impedance to the transmission line using this stub matching technique, which will cancel out the imaginary part of the load impedance uh, uh, that will be uh, that will be um, available between once we connect the transmission line to the load, right? So so the resultant impedance, once we have the load and the stub matching, must be equal to a real value, right? So the load impedance we can take as ZL, right? Load impedance we can take as ZL. The stub impedance we will take as ZS. So ZL plus ZS will be equal to a certain impedance value. We will take it as Z resultant, ZR. The ZR, if it is a value of like real plus J, some kind of a imaginary impedance, then that imaginary impedance, if it is available, if X value is more than 0, then the transmission line uh, will the connection between the transmission line and the load impedance is not fully matched. So if that is fully matched, then the value of the is a X must be 0. X must be made to 0. So what we are trying to do is, we are trying to add the stub and we are trying to make the resultant impedance a real value. So once we add the stub as an impedance, uh, and once the stub is in series, we can actually directly add the two impedances, and we can find the resultant impedance in terms of real part and imaginary part, right? So therefore we do not need to consider the admittances in here. The reason is, the stub is connected in series. The stub is connected in series, and therefore we need to only consider the admittance values, and we need to take the we need to consider the impedance values, and we need to consider the sum impedance value. Those stub is connected in series. Therefore, that is why we are um, in series. Stub is connected in series, and therefore um, we are going to take the resultant impedance by taking the sum of the two impedances. So we are just going to take the sum of the two impedances to find the resultant impedance, and then we are going to cancel out the imaginary part of the resultant impedance. Okay, so we don't have to write everything, but the reason is, basically the stub is connected in series, and therefore the resultant impedance is calculated by taking the sum of the impedances. Resultant impedance is calculated by taking the sum of the two impedances ZL and ZS. So resultant impedance is coming by taking the sum of ZL and ZS, and the resultant impedance's imaginary value can be easily identified using that calculation. Okay, so I hope it is clear to you. If it is not clear, please let me know. So basically, we need to consider the impedance Smith chart once we are designing a series stub matching. Okay, so series stub matching, we are going to consider the impedance chart. Series stub matching. Series stub matching. Okay. So in there, we are going to, as I said, we are going to point out the load impedance in the Smith chart. So once we have the load impedance, next step is to find the distance to the third step is to find the distance to the stub, distance to the stub from the load, right? So there are two options or two solutions that we can get. So we have the Smith chart. We have the position where we mark the load, right? We mark the load somewhere in the Smith chart. So we have certain point in the as the load in this chart, right? So we have marked a certain load point somewhere in here, let's say, and then now we need to draw the I mean SWR circle and intersect it at the 2 points in the unit circle. We need to take the radius from the center point of the Smith chart and we need to extend it to the intersecting points on the unit circle. So this is the unit circle. The unit circle value will be 1 plus j 1. So you'll be extending this point to the to 2 points in the unit circle, and there are 2 points that are giving us the distance to the load, distance from the load to the stub point. So these intersecting points are giving us the location where the stub needs to be placed in the transmission line. Okay, so if we take, for example, microstrip antenna case, or any kind of a strip antenna case, we can take the transmission like this. So if we have the load around here, load is in here, let's say, right? So load is here, and then we can we can measure the distance to the stub from the load point. So this is the load. From this location where the load is connected, we can find where the stub needs to be placed. So the stub needs to be placed, let's say it's here, so we need to decide the distance up to this point, right? So we do this in the Smith chart by first defining the load point, which we defined in here, right? This is the load point, and then we need to find the distance from this load point to the intersecting point. So intersecting point gives the location of the stub point. So there are two intersecting points, so there could be two different distance values. So the stub can be placed either in this D1 position or in D2 position. So this D2 position is also a possible solution. Okay, so D2 position is another possible solution to keep the stub. So there could be like two. I mean, I will draw the stub in the top position, just in case you might think like we need to change the direction of the stub as well. So actually, we connect the stub to I mean, this is actually this microstrip line denotes the top conductor of the this denotes the top conductor of the transmission line. So you can connect the stub to to any side of the transmission line. So anyway, basically you are just deciding the distance to the different to the two different stubs that you can place in the transmission line using these calculations. So D1, D2 can be decided. Okay, so the D1, D2 can be decided by taking the intersecting points in the unit circle. So intersecting points in the unit circle will give us these locations. So once you find the D1, D2, once the D1, D2 is found, next problem or the next challenge to solve is the length of the stub. So the length of the stub also can vary depending on the location where we place the stub. So these two stubs, they are not equal in length, they are different in length. So the different length values we need to find. So let's say this first stub's length is L1. Let's say this is L1. The second one's length is L2. So how can we find that length, right? So first, we need to find the impedance value at these intersecting points, right? We need to find the intersecting points in the impedance values in these intersecting points, right? Impedance at the intersecting points we need to find, right? Intersecting points. So the impedances must be found. So in here, the impedance value that we will get is like Z1, it will be like 1 minus J 1.33, and Z2 will be 1 plus J 1.33, right? So Z1, let's say, is here. Sorry, Z2 is here. Z2 is here because it must be 1 plus J 1.33, and this Z1 is in here where 1 minus J 1.33 impedance is there. So how can we find the length to the stub using these values? What should we do? I'm going to erase this part where we already discussed. Right, so in order for us to find the impedance value, in order for us to find the length of the stub, we need to decide what is the amount of impedance we need to add to this Z1 point in order to cancel out its imaginary part. Right, so if we take Z1, we can cancel out this impedance by adding how much of impedance? How much of impedance do we need to add to this impedance to cancel out the imaginary part? Yes, 1.33 plus 1.33 we need to add. So we need to add 1.33 plus 1.33 of impedance, 1.33 J, right? So J 1 plus 1 J 1.33 we need to add to cancel out the imaginary part of the to cancel out the imaginary part of the Z1 impedance. Okay, part of the Z1 impedance. Then we need to mark the J 1.33 line from the Smith chart, and we need to decide like the length of the stub starting from the short circuit or open circuit point in the Smith chart. So depending on the required stub, we will decide that length. So let's take, we want to measure the we want to measure uh, the length from open circuit point. Okay, so let's say that the series stub that is matched is an open circuit. That means like the stub that we will be placing on top of this transmission line, if we take this transmission line, we are going to place our series stub at a certain location from the load point. Then let's assume that we are going to place that series stub in with the open circuit at the end. Okay, with the open circuit at the end, right? So if we take, for example, it will look like this. So I mean, in the transmission line, it will have like two places where we will, where the stub will be constructed. Okay, so like we will have the transmission line, and we will have the like stub, right? So since it is a series, the stub will be placed like this. Stub will be placed like this. This part will be open circuit. This part will be open circuit. So we will have the load in here as usual. So the stub will be like this. The first point where the stub will be placed at is what we find as D1, and the stub will be placed in series like this. So um, so the in open circuit condition, due to that we will not connect these two stub endpoints. The endpoint of the stubs we will not connect. We will leave them as open circuit. So if we want to find the length to this length of this stub, then we need to take the length from the open circuit point to the intersecting point of the plus J 1.33 line. Okay, so plus J 1.33 line is found in the upper half of the Smith chart, right? So plus J 1.33 means like somewhere around here, somewhere around here. So we can draw the line that will intersect the outer circle or the boundary of the Smith chart, and then at that point you will get some kind of a you can you can find that intersecting point. You can find that intersecting point, and you can take the length to that intersecting point from the open circuit point of the Smith chart. So the open circuit point in the impedance chart is in here, right? Open circuit happens in here where the Z reaches infinity. So from this intersecting point, you can find the distance from this location up to the intersecting point, right? So once we find that, we will be seeing that the length is the length L1, like we will mark L1 here. L1 is around 0.397, right? It's 0.397 lambda, right? So we will ask, like, this is above 0.25, right? So the value is above 2.5. Oh, what is the reason, right? So in here, the open circuit, from the open circuit point, you are measuring the length towards the generator. So right, so open circuit point is here, so the length is measured towards the generator. Therefore the length is measured along this direction up to the intersecting point. So therefore the value of the length L1 is above 0.25, because this half a circle is equivalent to 0.25 lambda. Apart from that, we need to also add some other extra piece from this 0.25 lambda part up to this intersecting point. You can find it by taking the difference between these two points, right? So this point and this point. So once you add that value also, you will get a value equal to 0.397 lambda. Okay, so similarly, you can repeat the process for the case where you select the D2 distance. D2 distance, right? The second stop position that is possible, and then based on the D2 position, you can decide like what is the impedance value of that D2 position based stub. So the second stub will have a different length, and that length will be decided based on the impedance that it has at that point. So the impedance that it has at that point is Z2. Z2 is equal to 1 plus J 1.33. So since there's plus in here, what is the amount of impedance that we need to add to cancel the imaginary part of the impedance, of the total impedance, right? So we need to add minus 1.33 value. So we need to add minus means we need to add we need to consider the line which represents the minus 1.33 in the Smith chart. So minus 1.33 is represented by a line which is going in the bottom half of the Smith chart, and it will intersect with the circle on the circle of the Smith chart, the outer boundary at a certain location, and we will be able to find the length from the open circuit by taking the length from this open circuit position up to this intersecting point, right? So I will draw that in another color. So we will take this length as the length 2 from this open circuit point up to this intersecting point. So L2 will be given using this. So L2 value will be a lower value actually than the previous value. Okay, so L2 value you can find by taking the distance. By taking the distance from the open circuit position up to this point where we have the intersection. So that value has been taken as 0.103. Okay, so 0.103 has been taken as the L2 value. So you can check these values, and if you have any questions regarding these values, you can ask. So that is the solution of this problem, right? So as a solution of this problem, you can't give one solution, you have to give all the solutions, but you can select one of the solutions that you like based on your requirement and based on what is suitable for this application, right? So you need to actually, when you're designing, you need to, like, you can decide one solution, you can decide on one solution, but it's better to give all the possible solutions, and then out of them you can say, like, you can select the best one based on the application. Okay, so you need to anyway give all the possible solutions for this particular problem and these type of problems. Okay, so the output will be therefore like set of solutions um, which define the location of the stub and the length of the stub. So the solution will consist of L1, D1 and L2, D2. So the solution of this problem uh, will be giving the values of D1 and L1. This will be one solution. The second solution is like D2 and L2. So this is option 1, this is option 2. So depending on your resources availability and the feasibility of the fabrication, we can select the suitable option for our design. So most of the time we take the option where we have lesser lengths for the stub and lesser length for the distance from the load. So based on that, you can choose the option you like. I hope it is clear to you. If it is not clear, please let me know. If you have any questions, you can let me know. Also, I followed the example from the David Posa book. So you can follow that book also and check whether the procedure or the values that you have obtained are okay. And if it is not okay, then what is the reason? Likewise, you can study um, as well. Uh, So if you have any problems and you cannot understand some parts of that example, you can ask from me, right? You can anyway. The example is from the book from David Posa. If you have any questions regarding that example, you can ask from uh, us, and I will answer the questions. So next we are going to be talking about the double stub matching, right? So double stub matching uh, is another version of stub matching that that is used. So so far we have talked about like single stub matching types. So single stub matching types we have discussed. So in there we have discussed about a series stub matching and parallel or shunt stub matching. So basically single stub matching means there's only one stub which is placed along the transmission line. There's only one stub, like one set of, one stub, which will be placed on this transmission line. Right, so you will ask, like in series we have two stubs, but that also is considered as one stub. The series stub is also considered as one stub. So we have considered this kind of a scenario so far. But in cases where we need two stubs, we can create the two stubs in on the transmission line, and we can decide the length and distances to these stubs by using the Smith chart. So the length of these two stubs might not be equal. The distance between two stubs must be kept fixed. So the value of the distance or the gap between these two stubs must be normally kept fixed, and there will be like a standard value. So anyway, double stub matching is using Smith chart. Before that, double stub matching, you will ask like whether like double series stub matching is available, right? Double series stub matching is the other type of stub matching, right? So I hope it is clear to you. So just like single stub matching, double stub matching also can be done under double series stub matching, right? Double series stub matching, right? So double stub matching can be like divided into two: shunt stub matching and, right? So basically, double stub matching can be divided into two: shunt stub matching and series stub matching. Okay, so the shunt stub matching means like parallelly connecting the stubs to the load, right? So parallelly you're connecting the stubs to the load. So there will be two stubs, and there will be load. So the load is here. So the stubs that are connected will be parallelly connected to the load. In the series stub matching, then we have two like series stubs connected to the load, right? So in that case, like we have some like circuits like this where we connect two stubs in series to the load. However, like in general, we do not have the series stub based double stub matching in general. So this is not common. This is not commonly done. So mainly the reason is it's kind of infeasible and complex to achieve, and therefore people do not intend to use this more often, uh, so when compared to the shunt double stub matching. So shunt is the most popular one. So we uh, so most devices are using the double stub matching in the shunt manner most of the time. So the using Smith chart, you can actually do the stub matching or double stub matching. So it is actually a kind of a complex procedure than the single stub matching, and therefore you need to follow a lot of steps, and you need to find the final distances and the lengths of the stubs. So in here you will be having to find all the parameters, such as like the length and distance to the first stub, length and distance to the second stub, and so on. So D1, D2, right? And L1, L2, right? So there could be other couple of solutions. Another set of solution also can be obtained. So based on that, we can have like multiple solutions for this same design. So you need to uh, you need to decide all these parameters for one design, and therefore this is actually a little bit complex, and you need to follow the certain procedure in the Smith chart to find the solution. So you can give the solution D1. You can give the solution of the distance, solution in terms of finding the distance from the load to the connecting stub connecting point, the length of the stub, and then D2, distance to the second stub, and this length of the second stub. So this is going to be like a solution for this design, right? So I will not be doing the example related to that, but I will tell you basically the general procedure you can follow to find the uh, to find the uh, to find the I mean the distances and the lengths of the stub. Okay, so in this case, as you can imagine, we have another set of like distances and lengths of stubs. So this is like uh, this is uh, like there are I mean two options that you can follow. So this is also like a, therefore I mean a bit complex procedure uh, where you need to find the two sets of solutions. So anyway, like therefore I will only explain the procedure. You don't have, won't be going through like in detail computation. I will just mention the procedure that is normally used to find the double stub. So in there we will be doing that certain like specified procedure. So you need to follow that procedure step by step, and then you can find the stub values, right? The parameters of the stubs. So if you have the Smith chart like this, we can draw the unit circle like this. So unit circle will be going through the 1.0 point, and then in order to find the stub distances to the stub, first you need to find the place where the load point is. So the load point you are denoting using admittance in here. The reason is we are connecting the load in the stub will be connected in parallel to the load. So stub will be connected in parallel to the load. So therefore we are going to consider admittance values. So if you have the load impedance, then you can find the admittance value, and you can find the point of that admittance value in the Smith chart. So let's say that admittance value is in here. And then once you have this point, then the second step is that you need to shift this unit circle by certain lambda over 8 angle towards the in the anti-clockwise direction. So therefore, like in here you will be rotating this unit circle. You have to rotate this unit circle by lambda over 8. So once you rotate it, you will be having another circle which will be along this line. So if I think uh, I will erase this. So I need to rotate the unit circle by lambda over 8. Once I rotate it, it will be placed in here. So the final circle will be in this position, final position of the circle will be here. So once you have these two circles, now if you know the load admittance value, which will be around here, for example, then we need to extend this value of the admittance to these two circles. So you can extend it using a compass. You need to take the radius and you need to extend this point to this nearest circle, and you need to find the two intersecting points. So there will be 2 points. Let's say the Z1 and Z2. Sorry, not Y1 and Y2. So Y1 and Y2. So then um, then what you need to do is you need to take these intersecting points, and you need to extend those intersecting points to this unit circle. You need to then extend the points y1 and y2 until it intersects the unit circle. Okay, so right, so this is uh, this is just the procedure. So extend extend these points, extend these y1, y2 points until we meet the so this will be the third step, I think. Extend y1 and y2 until we meet the unit circle. So after we find the unit circle, then we can find the intersecting points on the unit circle by the y1, y2 points. So let's say those intersecting points by y1, for example, y1, if we extend, let's say that intersecting point will be along here, and the intersecting point of this y2 point on the unit circle, let's say, is along here. It will be another value which we will call as y2 dash. Let's say this is y2 dash. Let's say this first intersecting point as y1 dash. So once we are deciding the distances to the stub and the lengths to the stub, we need to find the distances from the considered open circuit or short circuit point up to this point. So if you are taking short circuit stubs, we need to find the location from the short circuit point up to the intersecting point on these circles. So in admittance charts, you have the short circuit in here. So short circuit point is in here. Based on this relative to that point, we need to find the length or distance to that intersecting point. So y1, right? So we need to find the position distance to that y1 position from the short circuit point. Okay, so you need to find the distances to y1 and y2 like that, and then also after that you need to find the distances to y1 dash and y2 dash, right? So based on that you can find d1, d2, d1 dash and d2 dash, let's say. So as I said, there are two sets of options, right? So therefore, like so the first solution, so I hope this is not confusing. So the first set of solutions will be d1 and d1 dash. Let's say this is d1 dash, and l1 and l1 dash, l1 dash. So the first set of solutions will be d1, d1 dash, d2 and d2 dash. And then another set of solution we can find by taking uh, d1, sorry, the first set of solutions will be d1, d1 dash, l1, l1 dash. Second set of solution will be d2, d2, d2 dash, l2, l2 dash. This is option 2. So we can find the distances to these intersecting points. So after that, by taking the admittance value at these intersecting points, you can find the value, that value of admittance you need to add. Based on that value of impedance, sorry, admittance that you need to add, you can mark that admittance value in the Smith chart and then find the length to that admittance point, that intersecting point, by taking the distance from the short circuit point to that intersecting point. So after that, you can find the length of the stubs. So the length of the stubs must be found for the two positions. So the y1 position and y1 dash position, right? The y1 position's length, I mean the length to the uh, length of the stub related to y1 position must be found, and the length of the stub related to y1 dash position must also be found by considering the amount of admittance we need to add to cancel out the admittance in these y1 and y1 dash positions, right? So it's actually a really little bit like advanced than the other methods that we discussed. So because of that, I just wanted to give an introduction to this part only. I will not be expecting you to solve this like in the exam. So you can, I mean, you can just know that series double stub matching can be achieved using Smith charts, right? So however, like if you want more information, this procedure is available in the reference book that I have provided to you, right? So I mean, you do not need to do the calculations related to this, but it's good if you know the procedure that you need to follow in this case. So that's about it for this stub matching section. So I have covered stub matching under the three different scenarios: a series stub matching, shunt stub matching, and a double stub matching. So if you have any questions related to that, you can let me know. Otherwise, you can leave now. So I think I'm going to finish now. So if you want, you can leave. If you have any questions, you can ask, right? I have covered these ones in these two classes that I had. So if you have any other questions related to Smith charts, you can come and meet me and you can get them resolved. So uh, that's about it for today. So thank you for attending. I will end the recording.